Let's construct the vertical decomposition using a randomized incremental construction. So what we're going to construct is the vertical decomposition as such. So the vertical decomposition of, and now we're going to have a set of line segments as input S and a bounding box R. But next to the vertical decomposition as such, we're going to also construct a search structure where the leaves of the search structure will correspond to the trapezoids, and the search structure will actually allow us to do fast point location. And we're going to use a randomized incremental construction. So the idea is very simple. We start with the bounding box, and then we're just going to insert the segments one by one. Every time we insert a segment, we're going to update the data structures, in particular update the vertical decomposition to again have the correct vertical decomposition. And adding these one by one, we're going to do in random order. Yeah, so we insert in random order, and we maintain both the vertical decomposition and the search structure. So let's have a look at how this will look like. So we're going to start with the bounding rectangle R. So that is our initial vertical decomposition, T0. And then after insertion of the ith segment, we will have this vertical decomposition Ti. And next to Ti, we are going to have Di, the search structure after inserting I segments. And initially D0 simply has one leaf, namely the bounding rectangle R. Let's insert our first segment. So let's say we insert S1. So here we have S1. S1 will result in 4 trapezoids, delta 1 to delta 4. And we're going to build a search structure that allows us to find, for a given query point, which trapezoid it is contained in. And this search structure will have 2 types of nodes, namely X nodes. So at an X node, we're going to test whether the point that we're querying with is to the left or right of that node. Yeah, so here we have a query point, and if we have an X node here, and the X node here is indexed by vertex of a line segment P1, then we're going to decide are we to the left or right of P1, and in this case we're going to the right, and that would mean that we're going to continue our search here. So at an X node we test left or right, and X node correspond to vertices of line segments. For this query point we will see it's to the right of P1. Then we have an X node for Q1. We see we're to the left of Q1, and then we end up at this Y node, and the Y node corresponds to a segment, and at the Y node we test are we above or below that segment. So I first see I'm right of this, I'm left of this, so I know I'm currently somewhere here. Now at the node S1 I'm testing am I above or below that segment. And when we do this test with the Y node, we always already know, or we guarantee, that at that point we actually know that a query point lies between the 2 vertical lines through the endpoints of that segment. And that is, or those are, the ingredients that we are using. So let's have a look at what happens if we add another segment. So let's say we want to add S2 here. So let's call that S2. So what happens when we add S2? So obviously this will destroy trapezoids of my previous vertical decomposition T1. I mean, it will destroy this trapezoid and that trapezoid. So those leaves will disappear here in my search structure. And instead I will need to build something else. So what I will need to do is I will need to update my vertical decomposition. That will look like this. And then I will have to update the search structure accordingly. So here's a small quiz. If you look at which node should come here. So which node will be the left child of S1? Will it be P2, so an X node with indexed by P2? Or will it be S2, so a Y node? Or will it be the face delta 6? It will be A, namely an X node with P2. So if I'm below, so after querying S1 here, what I know is that I'm in the following region. I'm in this region. When I'm in that region, what I will first want to find out is, am I to the left or right of P2? So am I here or there? So that's why I will have P2 here. And then when I'm to the left of P2, I can add delta 5. If I'm to the right, then I'm in this region here. Then I have to test above or below S2. So I will have S2 as node there. And then above would be delta 6. Below would be delta 7. And likewise, if I'm here, so if I'm to the right of Q1, I know I'm here. I first need to test, am I to the left or right of Q2? If I'm to the right, I'm in delta 9. If I'm on the left, I will have to test with S2, whether I'm above or below S2, and then I end up in either delta 7 or delta 8. So this is a search structure after inserting S2. What you see here is there were two ways to come to delta 7, so to the phase delta 7. So I could either be to the right of Q1 and end up here, or I could be to the left of Q1 and end up there. I only want to have one node for that trapezoid, which then means that I will have two edges pointing towards delta 7. That also means that the search structure that we have is not a tree, because I have two ingoing edges here. So it is a directed acyclic graph, and that's also why it's called D. What we will want to have is, we have the vertical decomposition, we have the search structure, and then we want to have pointers in between. In the vertical decomposition, we will also have these pointers between neighboring faces, and then for each trapezoid in the vertical decomposition, we have a pointer to the corresponding leaf. Now this allows us to do point location, because if I want to do point location, then, so let's do that. Let's have a point here. If that's a point that I want to find. So first of all, let's assume it is in the bounding box, because if it's outside, it lies in the outer face. That's an easy case. So if it lies in the bounding box, I know it makes sense to start searching here. I can test to the left or right of P1. I can test to the left or right of Q1. I can test above or below S1. I'm below. I can test left or right of P2. And this will get me to delta 5, or the leaf with delta 5. And then I have a pointer to the actual trapezoid delta 5. If this is now part of a planar subdivision, that trapezoid can tell me which face it belongs to. So this looks like that. I have the search path, I find the trapezoid. I then can find the corresponding face of the planar subdivision if I want to, by going to the edge below and finding that face. Now, what we have to think about is, how do we update these structures? So given delta I minus 1 and given ti minus 1, how do we add si? What we're going to look at next is how to update the vertical decomposition. So how do we go from ti minus 1 to ti? So I want to add this edge, and the first thing that I do is I will find the trapezoid that contains the left endpoint. How do I do that? I can use point location. So using point location, I find the trapezoid containing the left endpoint. From there, I want to find all trapezoids that are intersected by the segment, because those are the trapezoids that I will have to remove and replace by new trapezoids. So how do I find those? That is actually easy using the structure that we store with the vertical decomposition, because we actually do store for every trapezoid the neighbors. So if I found, using the point location data structure, I found this trapezoid, then by checking which of the vertical extension is intersected by the edge here, and note, since we were dealing with non-crossing edges, this edge can only go through one of the vertical extensions. So by finding this, so I'm checking the neighbors, by finding this, I will find from this trapezoid, I will find that trapezoid, from that trapezoid, I will find this one, this one, this one, and so on until I find the trapezoid that contains Qi. So I find all of these trapezoids, and these are the trapezoids that I will want to remove. If there are k trapezoids, let's say there are k trapezoids that I want to remove, then this will mean that, each trapezoid I can essentially at most cut in half, except for the first and the last one. So this delta 0 might kind of be cut in 3 pieces, same delta 7. But overall, if I have k trapezoids that I'm going to remove, I'm also creating order k new trapezoids. So these need to go out and they would be replaced by this. And that's how we update the vertical decomposition. We are in the middle of the randomized incremental construction of the vertical decomposition. We've seen how to update the vertical decomposition as such. Now we need to update the search structure. So our situation is the following. We have the vertical decomposition of the first I-1 segments, Ti-1. We have the search structure for the first I-1 segments, Di-1. And now the question is, how do we go from Di-1 to Di? So we know how to update the vertical decomposition as such. So we know how to go from Ti-1 to Ti. From that we also know which trapezoids need to be removed, which also means that we know which leaves of the search structure have to be replaced. So we can mark those. We can also create new leaves for the new trapezoids, and now we just have to link this up appropriately. And now we are in the situation that this new segment, so we had the new segment, and essentially it will have 2 vertical extensions. All the trapezoids that are in between, for those we need a Y node. So for those we will have to only need to decide whether we are above or below. So if we had, for instance, a trapezoid previously here that cut through here, now our new segment cuts it into 2 pieces, but we now just have to decide above or below. For the very first trapezoid and the very last trapezoid, we will first need to do left or right, and then only for the right part or the left part decide above or below. So that looks as follows. All trapezoids, all old trapezoids except for the last and the first one, get a Y node. Then the first one, so the leftmost one, gets an X node, Pi here, and the rightmost one gets an X node, namely Qi. And then this Pi, if I'm to the left, then there's only one trapezoid, so then I can link that up to the new trapezoid. And to the right, I will have the segment Si, so there I again will have an Si node and link it up appropriately to the trapezoids. And likewise here for Qi, the right hand side will link to a trapezoid, and the left hand side will link up to a Y node. Okay, so this is how things now look like, and that gives us the update for the search structure. So if we are updating Ti-1 and Di-1 to Ti and Di, when the new segment intersects a certain number of trapezoids, Ki trapezoids of Ti-1, then we are creating order Ki new trapezoids in Ti. We find those by first starting a search in Di and then linear time in the vertical decomposition. And then we can update the search structure as described just right now. What does that mean for the search structure as such? How does it increase? So in terms of how much deeper it becomes, the maximum is by 3 nodes. Can we actually get this depth increase in 3? So that's our next quiz. So in what case does the length of a path indeed increase by 3 nodes? Is it A, always, so in every time we update this happens, or B, only if the new segment is completely in one trapezoid of the old decomposition, or C, it only happens in degenerate cases? The correct answer is B. It happens if the new segment is completely contained in one of the old trapezoids. And the situation that we have then, so we have an old trapezoid. This is our old trapezoid. So if my new segment is completely inside, let's call this old trapezoid, let's call that delta. So delta was previously a leaf. This is now replaced by the following sequence. We first have an X node for Pi. Then on the left we just have one new trapezoid. On the right we now need to decide whether I left or right of Qi. Then on the right we just have one trapezoid. Then we have the Si here, and then the new trapezoids here and here. So in this case we had this increased by 1, 2, 3 nodes. But otherwise that does not happen, because if the segment goes through several trapezoids, these two nodes will not appear in the same search path. So far we looked at cases where we really have disjoint segments, but an important case, in particular in the setting when we come from a planar subdivision, is the case where we have two segments that share a common endpoint. So there we should just note that if we now want to, so the red segment Si is the one that we now want to search for because we want to insert it. So if that is the case, then we should search for the left endpoint of Si, so Pi. We should search for it in the search structure by slightly searching to the right. So far so good. Now we know how to update the vertical decomposition. We know how to update the search structure. Now before we formally analyze the algorithm, let's think about why we actually want to use randomization. If we think of the vertical decomposition, we already analyzed the complexity of the vertical decomposition, and that is linear, and that is independent of the insertion order. So for the vertical decomposition, the insertion order does not really matter. So this is not the reason we're doing randomization. The reason we're using randomization is because of the search structure. Because depending on which order we pick for the Si, the search structure may look different and it may have different complexity. In particular, the depth of a search path might depend on the order that we use for insertion, and also the number of nodes might depend on the insertion order. So let's think about the following questions. If I want to have a particularly long search path, so a deep search structure, what set of segments would give us that? And the follow-up question will be, how can I make the search structure as big as possible? But first, how do we get a long path? So we get a long path if essentially we already have a long path and we always make that longer, meaning the long path leads us to a trapezoid, and if the new segment is again in that trapezoid, the path gets even longer. So how could this look like? It could look like this. So in this setting, we are first inserting S1, and inserting S1, we have seen this structure many times, gives us this search structure. In particular, the trapezoid that sits here, that corresponds to what would be here. If we now insert the next segment in that trapezoid, then we get a copy, essentially a copy of this. We get a copy of this here. And then if we insert S3 here, we get a copy here, and so on. Every time, so if you look at this now, what we have P1, we have Q1, P2, Q2. So we have a search path of length order n. So we have a linear length search path. So in terms of point location, that is dramatically bad, because it means point location then would, for anything that is in that trapezoid down there, would take linear time. But if we use randomization, so let's mix up the order here a bit. So it's the same segments, but now I just picked a different order. Now you see that the search path will actually not get that long. So I mean, essentially now in this example, if S1 would be kind of the middle one, which is kind of maybe a lucky case, you could say, then we get a very balanced tree. So that means that the length of the search path depends on the order, and hopefully a randomized order can prevent these cases where we get very long search path. Now about the number of nodes. So why could the search structure have large complexity? So it could have large complexity if over and over, so if I have many trapezoids, which by a new segment, they all are split, and then by the next new segment, they are all split again. So how could this look like? So here's an example. We first insert S1, S2, S3, and S4. So that gives us lots of long segments here. So these segments, which are by now in my example have disappeared, would all be there. And then when we insert S5, we cut through all of those trapezoids and they become shorter, but still they go down to S5. So if I now put in S6, I again cut through all of those and again and again and again, meaning that every time I need to remove a linear number of trapezoids and I need to add again a linear number of trapezoids. And that means in terms of the search structure, every time I'm taking out a linear number of nodes and adding a linear number of nodes. So in each step of the insertion, the increase is linear, let's say linear in I. So I get something of order sum of I goes from 1 to n. So my search structure could actually have quadratic size, which is really not something that we want to have when this is exactly what we wanted to prevent when we went away from the slab decomposition. But also here, if I randomize my order, there's good hope that the complexity goes down drastically. So if I would have an order like this, simply are reversing the order, then all of the lower ones actually do not interfere with the previous ones. And somewhere in a random order, we would hope that we also get a reasonably nice case. And we're going to see that this is actually the case in the next video, where we analyze for the search structure the expected number of nodes and the expected depth of the search path.